Hi, my name is Hamza Hassan, and this is a quick walkthrough of my Applied AI coursework notebook, where I'll be exploring AI-based route planning for autonomous drones operating in mountainous regions, particularly in Nepal. So I'll briefly explain the problem, the data, the algorithms that I've chosen to use, and I'll demonstrate the system running inside of the notebook itself. So the first section, as you can see here, is part A. This is the application area review. So this is the motivation that I had towards the problem. So essentially, this project is based on robot and drone navigation, particularly in challenging areas. And I've chosen to use Nepal, knowing that it has mountainous regions and there might need to be aid transferred or aid moved across these regions. Um, so there are some constraints and problems which are brought with it. So, for example, they could be long distances, difficult terrain, knowing that there's a lot of weather conditions, bad weather conditions there, limited battery life in terms of the drones, and also I've seen through research that um, certain religious sites can't really be flown over. Um, so the next section, now across the problem, is the comparison and the evaluation of these three key algorithms that I've chosen. So I've chosen breadth first search, depth first search, and A search, which is three classical AI search algorithms. So BFS and DFS, they're uninformed search techniques, while A star is a cost aware, commonly used in navigation problems. So the goal essentially that I've set out is to evaluate which approach produces the most practical route for drone navigation. Now moving on to part C, where it's the implementation of this idea and of this problem that needs to get solved. So the data essentially in this project is intentionally predefined and controlled. So for example, I'll show you. Um, it's predefined through a weighted graph, which you can see here, and where each node represents a key location and each edge represents an estimated flight distance in kilometers. So here I've set a historic dictionary and I've chose to set them all to zero, um, which makes it behave more like a uninformed cost search. So this allows the focus to remain on an algorithmic behavior rather than just data processing or collection. So as you can see, I've chosen for zero. So in the prototype, I first didn't go for zero, but I added different numerical values. But I just wanted to make sure that A star is equivalent to uninformed cost search, which guarantees the shortest distance path on a weighted graph. So I made this choice deliberately to prioritize correctiveness and just avoid any heuristic biases that could be brought with it. So in the code, moving on to the search algorithms where I've implemented it. So the first is BFS. So here with BFS, it explores the graph level by level. BFS is it explores the level of all of the nodes in one level before it can go to the next level. Um, Whereas DFS is more about depth, so it explores the depth first, and which is here, and then lastly A star, which is a cumulative path cost to guide the search. So each algorithm returns a route from a chosen start location to the destination, which is landing point and launch point where the drone will be launched itself. So running the algorithms, if I can show you running the algorithms itself. Once it's run, we'll move on to the route comparison. So as you can see here, this essentially in this code, I've basically been able to see how, in terms of the main where we're going basically is from Lukla to Dolpa. That's the main example that I've gone for is Lukla to Dopa. So as you can see here, BFS provides that it crosses 2 stops. So Napche Bazaar to Dopa. So there's 2 stops overall. DFS is 4 stops. So it goes from Muktanaf, Gyokur Valley, Mananga to Dopa. Then A star is Mukanath, Johnson to Dopa. So essentially, this shows the amount of stops each algorithms would take based on this route that I've set out. And also here's just a code that I've actually used or thought to incorporate based on just to add some realism, because I've got to take into mind the weather, the altitude, the restricted airspace, battery limitations, and time dependency also. And there's a lot of factors that need to be taken into consideration. So here, for example, if I run this, it adds a constant random traffic delay. So constantly this delay will change. So this is just to add some realism to the code itself. And then here is the visualization itself, where it's plotted with coordinates that I've basically given, and I basically plotted it just to add some visualization of each algorithm. So this algorithm here would be BFS. So produce the string of shows the print statement of the path itself. So for example, if I change to A star, let's do A star actually. Let's do A star via A star. Let's just change the title. A star search, just for clearness. So this is the root of A star. It shows. Let's show now DFS. Remember DFS, there's much more stops. DFS, and then we'll go lastly back to BFS because I didn't show it clearly. And then here's DFS, and then lastly BFS. So breadth first search, BFS. So as you can see, it shows the route visually. So the plot basically shows a simplified map of Nepal. So these are cities that I've thought to take from Nepal. So this just helps validate the algorithm's output, and it makes sense, like geographically, not just numerically. Not just through the cities itself. So moving on to, let's look at the system diagram itself. Actually, should be, yeah, okay. So the system diagram. Let's go to my report. So the system diagram, as you can see, the user provides a start location, destination, and it chooses a search algorithm. Then the system would then access a predefined graph representing Nepal and the mountainous region of Nepal. Then based on the selected algorithm, a route is computed using route computation, the computation engine, which is here. Then after that, the system would give an output of the path, total distance, and a simulated delay, which is then visualized through a simplified map. So going back to the code itself, let's move on to, and just this is a quick summary. Let's move on to part D. So in part D is just looking at the software testing and the evaluation of the whole prototype. So as you can see, here's a graph where it compares the distances. So this the algorithms. You can see BFS 2 stops, 133 kilometers. DFS 4 stops, 141 kilometers. A star 2 stops, 58 kilometers. So in the evaluation section, I'm basically just looking to compare all of them based on distance, efficiency, and sustainability for drone navigation. And what I've realized through this is BFS and A star may use the same number of stops. However, the total distance differs, as you can see here, 58 kilometers compared to 133 kilometers is quite a lot. It's a big difference. So A star reduces the total travel distance, and I think I've stated the comparison between them both. I think it's around 56% if you compare both of them, which has a direct implication on even external factors like battery life and operational safety. Now, moving on to part E. Part E is where I just look at the diversity inclusion, so it's the EDI. So I also consider like ethical and sustainable factors later on, as I'll show you. But the system, mainly what I've wanted is that it avoids any bias. So it uses a transparent graph model. But it's important to actually take in the fact that there are some real world constraints, such as no-fly zones, as I said earlier, weather, and other factors. But from a sustainability, from an environmental sustainability perspective, shorter routes reduce battery usage and charging cycles, which could actually extend battery lifespan and reduce, even to an extent, electronic waste. So this is where I've compared it. And just to summarize, basically, this project just demonstrates how you can compare these three classical AI search techniques and how they can be applied effectively to real-world navigation problems. And what I've realized and what I've discovered is that while BFS and DFS are useful for comparison, A-star provides the most realistic solution for especially drone navigation in mountainous terrain. Thank you for watching.